Okay, so in next half an hour, I'm going to present some of the numerical simulations of fatigue crack growth in aluminum, not all welded constructions. My name is Aleksandar Grbović. I'm professor at the Department for Aeronautics here at the University of Belgrade, Faculty of Mechanical Engineering. And it's my pleasure to be here again as a lecturer at this DIF conference with my good friend, Professor Sedna, who is sitting right next to me. Okay, so I'm going to present some of the things and some of the calculations and simulations we carried out in finite element software, which is called ANSYS workbench, and software for XFEM, extended finite element method, ABAQUS. So objective of this presentation is to present advantages of numerical modeling. So I'm now going to remove this mask, so maybe you can hear me better now. Advantages of numerical modeling of fatigue crack growth in aluminum structures, especially welded constructions, under given loading using assumptions of linear elastic fracture mechanics. So all these simulations are based on evaluation. Evaluation of the fatigue life is based on evaluation of stress intensity factors and paths of crack growth predictions, which we can do using numerical methods, especially finite element method and extended finite element method. And finally, using these values of stress intensity factors and using some of the laws for crack growth, like Paris law, we can estimate the fatigue life of damaged structure. Here I'm going to present typical aerospace structures like wing spar and fuselage stringer panels. Okay, this is just a short reminder about how stress intensity factors are calculated within finite element software. So basically, we use interaction integrals in some form. You can see here one form of that integral here on the screen. And then using the values of this interaction integral, we can estimate stress intensity factors using a formula which you can see on the bottom of the screen. And in the recent versions of ABAQUS and ANSYS workbench, we can also use thermal and initial strains, as well as traction on crack surfaces in order to simulate the load that causes the crack growth to the structure. After that, after evaluating stress intensity factors, we can estimate the number of cycles that will grow crack to a certain length using some of the laws like Foreman equation or Walker equation, Nazgu equation as well. But typically we use Paris law, which is let's say 50 or more years old, but still very useful for these estimations. If we have mixed mode fatigue crack growth, in other words, if you have more than one load acting in one direction, so if you have loads in different directions, we can also estimate so-called equivalent stress intensity factor using the formula which you can see on the screen. And finally, the angle, so-called kink angle or angle of direction of propagation, can be estimated using the following equation you can see on the screen. And this equation is a part of these modules within ABAQUS and ANSYS that we can use to estimate directions in which possible crack will grow through 3D structure. Okay, usually in fatigue analysis, we start with the CT specimen experiments in order to evaluate coefficients for Paris law, for example. And here I'm presenting one of these specimens that we use here at the University of Belgrade to estimate Paris coefficients. And I also want to use, this typical experiment well known to all researchers who are dealing with fracture mechanics. The main goal of this here, why I'm showing you this experiment, is that recently in ANSYS, a new option was introduced. This happened like 2 or 3 months ago, where now we can apply variable load during calculation of crack growth through the structure. In earlier versions, we had to define maximum force acting, let's say tensile force acting on a specimen, and stress factor like this R here equals 0.1. And then using that maximum force and this stress ratio, we estimated the number of cycles. But using that approach in this particular case, so maximum force and stress ratio R equals 0.1, We didn't get a good fit with data obtained in experiment, but after we applied variable load in this sequence, and this is a load used in real experiment. So I had the access to the Excel file from that machine, and then I could take these values. So force was variable starting from approximately 10 kilonewtons and then increasing up to 19 kilonewtons in a final phase. So here I introduced force in 36 installments and then got very close, I mean, number of cycles to grow crack to 25, 26 or more millimeters, very close to experimental. So this was the evidence that, in fact, we need to define a load in a sequence or in a manner used in experiment or in real life if we measure, for example, this load during service, especially during service of aircraft. So this is important thing to remember because I'm going to back to this later in my presentation. So analysis of aluminum welded structures started with a structure which was not a welded structure. So this is a part of the wing which is called wing spar, made of aluminum, consisting of shear panel, which is a web, and flanges, which are caps. We call them caps. And usually in the traditional approach to aircraft design, we connect all these parts using rivets. And we call this differential spar. Of course, a very large number of riveted holes can lead to a large number of stress concentrators. And then there is a very high probability or possibility that crack will start to grow from one of these holes. In experiment with this SPAR, we analyzed the influence of these holes on the crack growth using sequences you can see here. First, we estimated where is a potential position of crack that might appear, and in a real experiment, we really got crack at expected location. So you can see in these images that location of the first crack was under this clamp, and location of the second crack, second crack started from one of these holes that we used to connect these caps to other parts of the structure. On the right hand side of the presentation, you can see how that SPAR looked like after approximately 60,000 cycles. So this was foundation of our research in welded aluminum structures. And first simulation using XFEM in ABAQUS was on this differential SPAR. We can see here on these images that the crack path that we obtained in these simulations was almost the same as crack path in a experiment. And that was the evidence that all these boundary conditions and all the other, things like, force that we applied, and here force, load was displacement at the end of the SPAR was in a connection with actual. But again, here we used maximum displacement as input, as a load, and the ratio 0.1, exactly the same ratio was, stress ratio was in experiment. And number of cycles estimated using Paris law and these stress test factors that we got in this simulation was very close to number of cycles that we obtained in experiment. So this was the evidence that complete approach was correct and that could be used in the next simulations. Then this is also part of that investigation. I just want to emphasize that in aircraft design, we use these spectra, as you can see here, typical spectra used in aircraft design. So these are, deformation or displacements measured on the tip of the wing during the flight of the commercial aircraft and during the flight of transport aircraft. And then using these spectra, we can estimate the total number of cycles in reality. For example, if crack grows here from this hole, it will be approximately 500,000 cycles. In this case, from the second, if crack appears in the second hole, it will be more than 6 million. And from third hole, it's almost 70 million cycles, which means that the most probable path direction here is from the first hole. And we got all these cracks in experiment on this first hole. Okay, then we turn our attention to integral structures. They're very popular nowadays in the aircraft industry. You can see here, for example, Airbus 380 These lower parts of the fuselage here, marked in orange color, they are mostly integral skin string panels. When we say integral, we mean welded structures. And the main difference between differential structure and integral structure net design, you can see on this image. So differential structure, for connection between two metallic parts, we use rivets, riveted joints, while on the other hand, for integral structure, we use laser beam welding, as you can see. Just to mention here, it's not part of this presentation, but probably will be part of some next presentation. We managed here to completely simulate this laser beam welding process. You can see I here put only these two images. So we simulated this laser beam motion and then analyzed distribution of the temperature through this stringer that you can see on the screen. Also, we estimated the heat effector zone. That's this image here on the bottom. And then we are also, our plan is, because I mentioned before that now we can also use as input, we can use thermal strains. And then we are going to estimate the influence of these residual strains on fatigue crack growth. I mean, this is our next project and we are actually working on it. Okay, so here we can see results from experimental analysis of these welded 4-stringer panels in Hamburg in Germany in 2005. Courtesy to researchers from this institute, we got some, but not all, experimental results from this experiment. This was project sponsored by Airbus, and you can see that the dimensions of this panel are 760 times 1,200 millimeters, and we can see these L profiles, L beams. In aircraft design, we call them stringers. So these are longitudinal elements, and they usually carry longitudinal force during the flight. So the goal here was to analyze the crack growth through the structure and to analyze the influence of stringers, the influence on reduction of the fatigue crack growth rate during the experiment. Again, we didn't have all results, but we used some of available results to estimate the accuracy of results we got in simulation. Also, you can see in the middle of the screen, this is so-called base plate. So researchers, in this institute, they use this base plate in order to estimate Paris coefficients. You'll see that on next screen. You can see here a base plate, 2 tension forces, and then they here estimated the number of cycles for 2 alloys, 61566 and 61564. In this presentation, I'll show you results of simulation that we got for this 61566, because for this alloy we had more data than for the other. And you can see here Paris coefficients estimated on the right hand side from this. We call this base metal panels. And first simulation, just to check these results and to compare boundary conditions and everything. We got this result, number of cycles. We can see that there is a difference about 10% between number of cycles in experiment and number of cycles obtained in simulation on the base metal plate in extended finite element method software ABAQUS. And that this was the first signal that definitely there is something here, let's say, not 100% accurate, because model is too simple. We have just one plate with a crack in the middle and two tensile forces. Someone might say the difference of 10% is not too big, but you'll see in next simulations that this difference started to rise. In parallel, we worked in a finite element software ANSYS workbench. Idea was to compare results using 2 different but also very similar methods of finite element method and extended finite element method. And you can see the crack growth in a base metal panel. And then we got a bigger difference using finite element method. Difference is, as you can see, 17%. Okay, I didn't emphasize this, but I believe that most of the listeners understand the difference between XFEM and FEM. Here you can see during the crack growth that a number of nodes around crack is increasing because the mesh is changing with every every step of the crack growth, as you can see. While in extended finite element method in ABAQUS, we have a mesh which is constant, so it's not changing during the simulation. So we wanted to compare these two methods and then to see is there significant difference. And definitely using the same boundary conditions, we got bigger difference. It's about 17%. I mean, compared to experimental. So this was a kind of alarm that maybe, but I cannot claim this, that maybe those coefficients evaluated in Hamburg maybe weren't so precise. That's one possible conclusion. Conclusion number two, maybe in that experiment something, but honestly, I don't think that such as in Hamburg didn't know how to carry out the experiment in the right direction, but probably again here in all these experiments, in these simulations, I'm sorry, you can see here this is the only info that we had about force. So maximum force 115 kilonewtons and ratio 0.1. So in our simulation we applied constant force and then define this ratio, and this is what we got. Probably during experiment there was a slight change, or maybe bigger or smaller change. I don't know. I don't have info about that. During the experiment, just like in that example with the CT specimen that I showed you 10 minutes ago. So maybe if we could have results from experiment, I mean, in some form of Excel table where the results of forces, I mean, values of forces through experiment, maybe we could get better, I mean, fit. So after this experiment with base metal in Hamburg, they studied the plate with 4 stringers, as you can see here. And again, here in this case, we only had not force, we had maximum stress, normal stress in this direction. And this is what we used in IPO. Of course, we converted this stress into force and then used the same ratio. And experiment number 3 was with clips. What are clips? Clips are additional elements welded to plate in order to slow down the crack growth. This is one of typical actions or typical methods used in aircraft design. One of the methods is if they spot during some break between 2 flights, let's say, if they see crack on the wing, let's say. So one of the methods is just to drill a hole through the tip of that crack to slow down the crack. If they have more time, they use these clips, I mean, to weld them for structure, or simply they weld the crack. And also we had one presentation about that to analyze the crack growth through welded crack. So clips are here used to slow down the crack, and we decided to make simulation with 4 stringers and 4 stringers with clips, with 3 clips, in order to see what's going on. And on this next slide, you can see here in the middle, you can see this video where crack is going from the middle. Exactly the same experiment was carried out in Hamburg, and during this crack growth, you can see that crack is approaching these stringers, destroying them, going through them. This image on the screen is correct, but here on the wall it's not. So in order to analyze the influence of the mesh size on a number of cycles, we made 3 different models. One model with a very small size of mesh, 1 millimeter was the average size. The second was 2 millimeters, and finally 4 millimeters. And you can see here this bottom image that in the case when we had a mesh of 4 millimeters average size of the element, that crack length was 300 millimeters, more than 300 millimeters in 278 steps, and almost all 4, you can see, stringers have been destroyed during this simulation. Exactly the same thing happened in experiment. But results that you can see on the next slide, results, I mean, comparison of a number of cycles obtained in these simulations and number of cycles in experiment was disappointing. As we can see here, 39% was when mesh was fine, only 1 millimeter was size of the mesh, and then difference is decreasing with increasing mesh size. So 32% for 2 millimeters and 31%. This was the best result that we got. The difference of about 30% between, I mean, experimental and numerical, let's say, experiment. Difference is, of course, very large. The only thing, good thing is that we are on a safe side. I mean, the simulation predicted the lower fatigue life, I mean, shorter fatigue life in terms of number of cycles to reach this crack growth. We can see also on this, the right-hand bottom slide, that when we compare, because this is what I got from Germany, and could compare the crack growth rate, and we can see that during first, let's say, I don't know, maybe 50,000-60,000 cycles, that crack growth rate in experiment and in simulation was almost the same. And then you can see here that crack growth rate in simulation is greater than crack growth rate in experiment. So this is explanation for this difference, which is increasing and increasing with crack growth. The same thing we did in ANSYS using finite element method, where these, I mean, cracks with, I mean, adaptable mesh. And we did here a simulation with stringers and simulation stringers plus 3 clips, as you can see here on this biggest simulation, 3 clips. And didn't get better results. In fact, in the finite element method, we got again difference about 31%. So using XFEM or using FEM, obviously results are very similar, almost the same. But there is a difference between experimental and this results. We didn't have results for clips. So here on this slide, I just put comparison base metal, stringers, and stringers plus clips. And we can see that clips, they increase, according to simulation, they increase the life approximately by 5%, which is not so big increase if we compare this to total number of cycles, but there is increase when we use clips. Okay, so after we finish this investigation, of course, this is still ongoing investigation, because we are now trying to make some adjustments. Okay, not to the model, because model cannot be, but maybe to incorporate this influence of maybe some additional strains or thermal strains, to see maybe the influence of the welding. But I believe that after welding they use some I mean methods for stress release. But I want to show you this because I started with wing SPAR, and I want to finish this presentation with wing SPAR. So idea was here, you saw what happened to differential SPAR. So here idea was to replace differential SPAR with integral wing SPAR, to use welding. I mean, to make this SPAR, not to use rivets to make all these joints. And idea was to keep the weight or mass of the SPAR constant. So this is why we fix here the cross-sectional area of the SPAR, but we change, as you can see, cross-section, and we analyze 3 different types. And all these 3 types are used in aircraft design. So this is I-beam, then this in middle is U-beam, and finally I-beam with an intermediate flange, as you can see here on the screen. And we wanted to find here, especially for this flange, we used optimization method in order to find optimal values for B1, B3, I mean all these dimensions, in order to get the longest possible fatigue life. And again, we use the same software, ABAQUS first. You can see here displacement 3 millimeters, exactly the same was the maximum displacement in experiment, initial crack position. So this is where crack appeared in experiment. And then if you compare only integral or welded wing SPAR to that differential, we have approximately 6 times longer fatigue life, because here for same Paris coefficients we got 360,000 cycles compared to 60,000 cycles in experiment. Even better results we got for this I-beam with this intermediate flange. Interesting thing is that U-beam results for U-beam are worse than results for I-beam. Okay, we have explanation for this, but I think we don't have enough time. Maybe some next presentation will be about that. So the best option is to make, and of course we optimize here. You can see three different C1, C2, and C3 cases because we use using optimization methods. We got three so-called best options, and then we tested all three and got for this version C3, we got 1.4 million cycles compared to these 60,000 cycles for differential SPAR. And then the same analysis carried out in ANSYS. Again, we wanted to check are these predictions for example, when we have two cracks, growing at the same time. You will see here, this first video is for one crack, which splits and then moves into perpendicular directions. And then finally, the second video, we have two cracks growing at the same time and then almost connecting at the bottom of this I-beam. And then when we compare to this integral wing spars, welded wing spars to differential, we can see huge difference. Number one, you can see here that in differential, the same geometry, the same I-beam, but this is welded spar, and this is estimated number of cycles. In reality, this is, as you can see, for integral SPAR, more than 2 million cycles, approximately 2 million cycles, and for differential, we saw something about 500,000 cycles for differential SPAR. Also, when we compare these images, we can see that crack paths predicted by both XFEM and FEM almost the same. And that was also the evidence that all these boundary conditions, if they're well applied, they will be in correlation not with each other only, but also in correlation with the experimental crack growth. And to conclude this, if you talk about these clip panels and the stringer panels, 4 welded stringer panels and 3 clip panels show improved fatigue fracture performance compared to base metal. So we saw that base metal plate was around 200,000 cycles, but in a case when we have 3 clips or 4 welded stringers, we have more than 100% improvement. I mean, compared to this. Also, we can conclude that both XFEM and FEM give good predictions of the possible crack growths. I mean, growth paths in a structure. Definitely, welded structures, and talking about aluminum welded structures, have longer fatigue life than differential structures. So even if we compare just welded with differential, we saw that in experimental investigation, a number of cycles was longer, and this is the problem that we are still working on. Why this significant difference of about 30%? But as I said, good news is that we have underestimated fatigue life, which means we are on the safe side. These are questions for further study, technical force during the experiment. But to do this, we must have, especially for these stringer panels, we should have values from experiment, Paris coefficients, because we just took them from that presentation, and we don't have any evidence about good evaluation of Paris coefficients. And finally, okay, there is still some room maybe for numerical model improvement, but honestly, I think that we cannot improve this more, because that's more or less all. Okay, in one investigation, we also used welded toe, but in order to simulate the piece of the metal left after welding, but we didn't get a big difference. But also properties of that toe maybe should be analyzed. And finally, experiments are still necessary for numerical model verifications, but once model is verified, it can be used for analysis of alternative designs, which reduces, of course, costs, and then decrease the time to market. So if we're working on a new model of the aircraft, we want this time to market to be as short as possible. So numerical simulations are good alternative to experimental approach.
Okay, that's all. I hope that I was, yeah, wrong.
Almost on time.
On time.
Thank you. Thank you very much. Are there any questions, please?
I would like to ask one question, please.
Yes.
First, my congratulations for your excellent work. I think it's a very complex model in the huge number of load cycles. I think it's not easy to model such a thing. One question, my question is concerns the crack closure modeling. You are not modeling crack closure, correct?
Yes. Yes.
Maybe that can explain the difference between the numerical prediction and the experimental results.
Yeah, probably. So this is one of the options on the table, definitely. Yes, for further investigation. Yes.
And is it possible to include the crack closure in the
at the moment? I mean, talking about these commercial versions of ABAQUS and ANSYS, until let's say a couple of months ago, we couldn't do that. But now part of the code, I'm talking about ANSYS because most of these newer simulations we carried out in ANSYS, it's partially open, and now it's possible in using Python to define some codes and adjust these models so crack closure could be included.
Okay, thank you.
Thank you, Fernando. That was excellent suggestion. Any more questions? If not, once again, Aleksandar, thank you.
Thank you.